Hello, everyone. Today we are to derive the momentum theory of a rotorcraft. Let's assume from the schematic given is a rotorcraft steam tube with a varying cross section from A to BC and D, where the BC form the rotor disc. Now, by using the thrust equation, that is the product of the variation of the pressure on the rotor disc, PC minus PB multiplied by the area of the rotor disc, ABC. That gives us PC minus PB pi r squared. That is the area of the rotor disc equals pi r squared. And also the equation for thrust also equals the product of mass to the variation of the velocity from end of the steam tube to the other far end. That equals m, the product of ud minus ua. So let's assume this is equation 1, this is equation 2. Now, looking at the cross section of the rotor disc, and based on the assumption of the momentum theory, the velocity at the rotor disc on the B section and the C section equals the same. So therefore, UB equals UC due to the thin section of the rotor disc, and which equals UA plus V1, that is the induced. The V1 equals the induced velocity. So therefore, as UB equals UC at the rotor, also the equation equals UA plus V1. That's equation 3. Also, UD on the other side equals UA plus V2. That's equation 4. That is the induced velocity at cross-section UD equals UA plus V2. So therefore, the last assumption is PD equals PA, that is the pressure from the far end of the tube equals the same. So therefore, PD equals PA. That's equation 5. Now we have 5 equations based on the assumption of the momentum theory established. Now, using the Bernoulli equation, that is by integrating Bernoulli equation into the momentum theory equation, using all these established 5 equations, we can establish that half rho v squared plus p equals constant. And that's Bernoulli equation. From there, we can integrate it to the cross section of A and B. That is this particular side and this particular section. Don't let us forget this is AB and this is CD. So by applying the integration of Bernoulli equation to this 2 cross section of the windmill tube, we can derive that half rho UA squared plus PA equals half rho UB squared plus PB. That's for section AB. Also, we can also say half rho UC squared plus PC equals half rho UD squared plus PD. That's for section CD. From this particular equation, we can single out PC. How do we single out PC? Our PC equals half rho UD squared plus PD minus half rho UC squared. Also, we can single out PB. So our PB, that is PB, we've already derived PC, so now PB. PB equals half rho UA squared plus PA minus half rho UB squared. And if that should be the case, the next thing is to single out PC minus PB. And how do we do that? So therefore, our PC minus PB equals half rho UD squared plus PD minus half rho UC squared minus half rho UA squared minus PA plus half rho UB squared. And don't let us forget that PD and PA equals the same. Where PA equals PD. Then PD and PA cancel each other. Also, we know that UB equals UC, that is, the velocity on the rotor disc are equal, which is UB and UC. So therefore, half rho UC squared cancel each other, and half rho UB squared cancel each other. So the remaining equation equals PC minus PB equals half rho UD squared minus half rho UA squared. PC minus PB equals half rho UD squared minus half rho UA squared. And don't let us forget that UD equals UA plus V2 from the previous equation. So by slotting it into this particular equation, you can derive that PC minus PB equals half rho UA plus V2 squared minus half rho UA squared. So that becomes half rho UA squared plus 2 UA V2 plus V2 squared minus UA squared. And if that should be the case, that becomes half rho 2 UA V2 plus V2 squared, which becomes half rho 2 UA plus V2 V2. Which is PC minus PB. And don't let us forget that the thrust equals PC minus PB to the product of the area of the rotor disc, which is PC, and it equals PC minus PB pi r square. Now, by slotting this equation into this, we have our thrust to be half rho 2 UA plus V2 V2 pi r squared. Now, by deriving the time derivation for the both side equation, using the equation of derivative of a thrust to time, that gives us UD minus UA over dt. So therefore, the thrust equals dm dt UD minus UA, which equals the mass flow rate UD minus UA. And if that should be the case, the mass flow rate equals rho A of A to the product of U of A equals rho A of B to the product of UB equals rho A of C to the product of UC, which equals rho A of D to the product of UD of all the cross section. And don't let us forget that again. AB equals AC, which equals pi r squared. So now our momentum theory now becomes the PC minus PB from the previous equation, which equals half rho 2 UA V2 plus V2 squared. It now becomes half rho 2 UA plus V2 V2. So the thrust will now be half rho 2 UA plus V2 V2 pi r squared, which equals rho pi r squared UA plus half V2 V2. So by slotting the value of the mass flow rate, that is P rho AB UB and rho AC UC, we can derive that thrust equals rho pi r squared UA plus V1 V2. Now, by comparing or juxtaposing two of these, juxtapose the equation, can derive that the half of this one equals to the V1 of this one, and all other equation equals the same. So that means that V1 equals half V2. That is, the induced velocity from the rotor disc is half of the velocity at the free end of the rotation of the rotorcraft. So therefore, C now equals rho pi r square UA plus V1 2V1, which equals 2 rho pi r squared UA plus V1 V1. So the total thrust in summary becomes 2 rho pi r squared UA plus V1 to V1. QED. Thank you very much for staying tuned.